Let's say you have this neural network and a dropout layer in between with a p of 0.5, which means during training, dropout randomly turn off half of the neurons. Let's take this example input and weights where this is your data, and since we are using p of 0.5, which means only 2 of them in the network will be active. And let's take random variable z from the distribution. So without dropout, the output will be this. But during training phase, since only 2 inputs are receiving from previous layer, the output will be this. Now here's a clear difference between what network learned during training when dropout was active and what it is predicted at inference when dropout get disabled. So how the network avoids this difference? This is a very basic question about dropout layer. So let's understand why the network behaves consistently at inference time. During training, dropout randomly turns off some neuron. For each unit in a layer, the output will be this, where this is the activation before dropout, and z is the random variable that is 1 with probability p and 0 with the probability 1 minus p. This means each forward pass uses a different thin subnetwork where only a random subset of neurons are active. Then the number of subnetwork will be 2 to the power n. At test time, you obviously can't average all those 2 to the power n possible networks. That's computationally impossible. So here's an approximation trick that gives you the expected output of this ensemble using just one deterministic network. At inference time, we use the full network but scale each neuron's output by retention probability p. This is known as weight scaling inference or equivalently activation scaling. Now let's apply this trick on this example. We know at training time the network learned this value from given input and waits when dropout was active. So at inference time, we don't drop any neurons, but we scale activation by the retention probability p. Then the output is this. But wait, this is not looking great. The prediction is far away from 8.4. So why is that? Because we have only trained the network for one single time where the possible random variable chosen from dropout was this. But we know we train network for several epochs. So let's say even if we train it on the same input for 3 epochs, then the result will look something like this. Then the average will be 6.2. This is much closer to 5.1 than 8.4. Similarly, when you train network for longer, more combination of random variable will get covered from distribution and the result will be correct aggregated output. For example, if you train for one more epoch and luckily get this random variable from distribution, then you'll get this output. And when you take average of that, you'll get 5.1. And that's the complete working of dropout layer. So here are 3 things you can take from this video. During training, dropout injects noise. This makes neurons work harder individually, learning features that are useful independently of specific other neurons. At test time, you average all those noisy subnetwork by scaling, giving you more stable and smoother model. This is a form of approximate model averaging that improves generalization. Thanks for watching.